Hello and welcome to another geometry lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 7, Lesson 7 on more similarity reasoning. In the last lesson, we saw how to do a similarity proof, how to prove two triangles were similar, primarily with the angle-angle theorem of similarity. Today we're going to extend that a little bit further, but before we do, we need to take a look at something that's important about fractions. So let's get into that right away. An important property about fractions. In this lesson, we will extend our reasoning with similar triangles to include relationships between their side lengths. First, we need to review an important property of all fractions. This is what is known as the cross product property of fractions. If the cross products of two fractions are equal, then the fractions are equal. Conversely, if two fractions are equal, then their cross products are equal. Now, you use this property all the time. You used to use it back in middle school and elementary grades to just test whether or not two fractions were equal to each other. But you also use it all the time when you solve proportional equations by doing cross multiplication. Anyway, let's use the first part of the cross product property to just do exercise number 1. In each case below, test the equivalency of two fractions by seeing if the product of the means is equal to the product of the extremes. And I'll kind of explain that phrase in a little bit, but basically that just means by using the cross product test. Now the cross product test says, okay, look, if I'm trying to figure out whether or not 3/6 is the same as 1/3, what I'm going to do is I'm going to do these cross products and I'm going to see whether 3 times 3 is equal to 6 times 1. 3 times 3 is 9, 6 times 1 is 6, so the answer there is no. All right, so if that cross product was equal, then the two fractions would be equal. In this case, it isn't. Why don't you pause the video now and see which pairs of these fractions are equal and which are not. All right, well, let's take a look at letter B. In this case, we've got 3 times 12 is equal to 6 times 6, maybe a little question mark there. 3 times 12 is 36. 6 times 6 is 36, so the answer is yes. Now, before we move on and take a look at letter C, if you're sitting there as a student and you're saying, well, look, I know 3/6 is equal to 1/2, and I know 6/12 is equal to 1/2, so I don't need to use this test. That's totally fair. I get that. The point here isn't to rehash 4th and 5th grade math. It's not that. The point here is to just kind of get you used to the idea that I can take a true fraction like this and turn it into a product like that. Anyway, let's go on to letter C, right, where we have the 6/4 equals 15/10. If I do 6 times 10, and I see whether or not it's 4 times 15, 6 times 10 is 60, 4 times 15 is also 60, and so yes, those two fractions must be equal. Let's take a look at one last one. Here I have 4 times 12 is equal to 6 times 9. 4 times 12 is 48. 6 times 9, though, is 54, so in that case the answer is no. Teachers often employ these in early grades in order to help students determine whether or not two fractions are equal to each other. We're going to use this idea, though, within similarity proof. Now, this gets into changing a proportion into a product. And again, understand that term, a proportion. A proportion is simply one fraction equal to another fraction. Now, in many similarity proofs, we're going to want to change a proportion into an equivalent product by rewriting it with cross products. Whenever we do that, we will use the following line of reasoning. So you know, in proofs, you always have a statement, and then you always have a reason. So whenever we have something that looks like this, A over B equals C over D, and we change it into B times C equals A times D, we're going to say that the product of the means is equal to the product of the extremes. When you have a proportion, technically, the top of this fraction and the bottom of that fraction are called the extremes, and the bottom of this fraction and the top of that fraction are called means. Why that is, we're going to kind of get a sense for a few lessons down the line, but for right now, I just want you to know that if you take a proportion and you change it into a product within a proof, your reason's going to be the product of the means equals the product of the extremes. Let's see how that works in exercise number 2. In the diagram shown, ABCD is a trapezoid with segment AB parallel to segment CD. Diagonals AC and BD intersect at point E. We want to show that AE times DE is equal to CE times BE. Letter A. Mark all congruent angles based on the parallel lines. All right, so I'd like you to pause the video right now, right? We were told that AB is parallel to CD, and I'd like you to mark congruent angles on this diagram that we know are congruent based on those two lines being parallel. Pause the video now and take a moment to do this. All right, well, we're talking about alternate interior angles here created by these parallel lines and the two diagonals. So, for example, this particular angle is congruent to this particular angle, and this particular angle is congruent to that particular angle. Okay? And we know that. Again, they're just alternate interior angles. They're the angles of the Z, if you like. They're the Zorro angles. You probably don't even know that reference. Anyway, let's take a look at letter B. What two triangles can be proven similar using the angle-angle criteria? State them and draw them below in similar orientations. All right, well, it should be pretty obvious based on this picture. Pause the video now and tell me what two triangles are similar based on the angle-angle criteria, and then we'll work together on drawing pictures of them. All right, well, clearly it's the triangle up here and the triangle down here. Now, I'm saying it that way instead of giving their names because it's very important when we write a similarity statement that we have the corresponding vertices match up in our two triangles. So I'm going to write down triangle ABE. All right, so triangle ABE is similar to triangle. Now we have to get this right, okay? And one of the keys is looking at those angles. Notice I have a single arc here and a single arc here. That means that A is corresponding to C, right? So I've got that. B has got a double angle mark here, or a double arc mark there, and D has it down here, so that's going to be D. And then, had I done it, right, I could have put 3 marks here and 3 marks here for that pair of vertical angles. I don't need to because it's the only letter that's left, but I'm going to do that. Triangle CDE. So I've now got my statement. I now want to draw the two in equivalent orientations, all right? And that's just helpful because it helps me then see the sides that correspond to each other. Now, I like a triangle to be like sitting on a horizontal side. So I think I'm going to actually draw triangle CDE exactly the way it is. All right, I'm going to kind of draw this one sort of out like this with D here, C here, E here. And I'm going to actually, again, mark these angles because it's going to be helpful. Whoops, don't want that because it's going to be helpful for me when I draw ABE. Now remember, two similar triangles always have the same shape. So I'm going to try to draw a sort of smaller version of this thing right over here. Okay? Now keep in mind, right, wherever C is, that's where A has to go, right? So A is actually going to be sitting right down here. All right? Likewise, wherever D is, that's where B has to go, right? They've got the same arcs. So we're going to put this here, and then my final vertex is there. Right, and then what that does for me is it really helps me see the corresponding sides, right? AB corresponds to CD, BC corresponds to DE, AC corresponds to CE. Okay, let's take a look at the last little part of this, letter C. Once you have proven the triangles from B are similar using the angle-angle criteria, you can then finish the proof. Fill in the reasons for each of the following statements. In other words, right, I want to ultimately prove that this product is true. So what I can do is I can say now that BE divided by DE, why am I not even seeing BE divided by DE? Did I draw this wrong?
The little one should have an E, I think.
Oh yeah, the little one should have an E in it. Why do I have a C there? Why do I have a C there, Joey? That doesn't make any sense. Whew, that's much better. I'm like, there's no BE. Okay, so BE divided by DE is equal to AE divided by CE. Now, what is my line of reasoning when I do that? The line of reasoning is that corresponding sides of similar triangles are proportional, right? So BE corresponds to DE, and AE corresponds to CE. So when I divide BE by DE, that must be the same as when I divide AE by CE, and the reason there is corresponding sides of similar triangles are proportional. Now I just, do a cross product, right? So I say AE times DE is equal to CE times BE, and my reasoning there will be the product of the means is equal to the product of the extremes. By the way, if you said the product of the extremes is equal to the product of the means, that would also be great. There'd be nothing wrong with that, okay? But you're going to see these two lines of reasoning, one right after another, in both of the proofs that we do on the back side of this worksheet, okay? Now, almost all these proofs are going to be all about proving two triangles are similar, then going on to set up a proportion, and then turning that proportion into a product. So let's get into that a little bit more. These types of proofs are similar to CP/CTC proofs, right? Except first, we must prove two triangles are similar, not congruent. So remember when we do CP/CTC proofs, we're trying to prove two segments are congruent or two angles are congruent, but first we have to go through and get two triangles are congruent before we can then do the CP/CTC. This is very similar. Once we have proven two triangles are similar, we use these to set up a proportion and then turn the proportion into a product. These types of proofs are very common when we get to our unit on circle geometry. Now that won't be until unit 9, so it's a ways away, but we need to have this kind of reasoning down pat before we get there. So let's look at a simple example of this type of proof. Exercise number 3. Given segment MNQ, segment MPR, and segment NP is parallel to segment QR, prove that MN times MR is equal to MQ times MP. All right, now let's take a look at this. First, let's think about what two triangles we could possibly prove similar. And that's all about NP being parallel to QR. Right? So I've got NP parallel to QR, right? And that's going to tell me that this angle is congruent to that angle because they're corresponding angles. It'll also tell me that this angle is congruent to this angle because they're corresponding angles, right? I could even have the fact that angle M is congruent to itself. Regardless, what I will be able to do is I'll be able to prove that triangle MNP is similar to triangle MQR. And maybe I'll bring these arcs in like that. Right, and get rid of that. So once I've got that proof down, either by using these two pairs of angles or, bringing in angle M, I can then work on setting up this ratio. Now, what's kind of important is knowing which ratios I'm looking at. This is where it's very helpful to kind of have our highlighter going, right? Whoops, that's not what I want. I actually want to choose the highlighter, Kirk. Okay, so let's go back, choose it. I think I've got it. All right. Right, I've got MN, and I've got MR, and I've got MQ. I'm going to highlight those both in purple. And then I think I'll go over here and go with aqua or something, I don't know. And then I've got MR and I've got MP. Right, and you can really see in this case, you can already see how we're going to use these two similar triangles. Eventually we'll say something like MQ divided by MN is equal to MR divided by MP. So let's see how this plays out in a proof. before we get to a tough one. All right, whoops, that didn't work at all. I've got to get back to here. Okay, there we go. Now let's try it again. All right, first statement, all of my givens. I'm going to do a given dump, right? I've got these two collinear givens, then I've got my parallel given. Easy enough. Now let's start to establish some angles being congruent. Angle MNP is congruent to angle MQR, right? That's these two angles. Reason? Corresponding angles created by parallel lines are congruent. Easy. All right. Now I'm going to go grab that shared angle. Angle M is congruent to itself, right? So at this point what I'm doing is I'm going with this approach instead of this approach. So I'm using that shared angle. Again, it doesn't matter whether I use these two angles based on parallel lines or these two angles and then these two, based on that shared angle. Here, I'm going to go with that shared angle, and I've got that due to the reflexive property. Okay, now I've got triangle MNP similar to triangle MQR. And it doesn't matter what the order of the vertices on the first triangle are, as long as the ones on the second one correspond, right? So if I'm going to go MNP, then I've got to do MQR. I could also do like PNM and then do RQM. It doesn't matter, they just have to be the corresponding vertices. Now the reason is, hello, come on. There we go, the angle-angle similarity theorem. It was shy, it didn't want to come out, that reason. The angle-angle similarity theorem. Okay, right? All of that is the equivalent of proving two triangles are congruent, except now we've proven two triangles are similar. So where are we going now? We have to keep our eye on the ball. This is the product we want. So now we just have to set up a proportion that involves the two pink sides and the two, let's say, aquamarine sides. I don't even know what color that is. Here we go. So we're going to say MQ divided by MN is equal to MR divided by MP. Again, MQ divided by MN is equal to MR divided by MP. And the only reason that we're not getting QR and NP involved is that they aren't in the product that I'm trying to prove. If they were, then I would get those two sides involved, but they're not. And I say corresponding sides of similar triangles are proportional. Finally, I now want to turn this into my desired product. MN times MR is equal to MQ times MP, and that is the product of the means is equal to the product of the extremes. That's it. That's my whole proof. So pause the video now and write down any of these steps that you might need to. All right. Now these kind of proofs can be especially challenging for students because your final result is a product. And you really kind of have to work backwards to think about, all right, well, what is my proportion that will give me that product? What are my two triangles I have to prove similar in order to get that proportion, etc., etc. Let's look at a more lengthy example of this. Exercise number 4. Given ABCD is a rectangle, points E and F lie on segment AD and BC such that segment EF is perpendicular to segment AC, prove that AC times FG is equal to CD times CF. All right, letter A. Use the product above to determine which two triangles will need to be proven similar. Outline a strategy based on the givens. All right, so many times when you're on a state exam or a local exam or whatever, you're just going to have to prove it, right? What I'm trying to do right now is walk you through how to make that a little bit easier. And the first thing that I'd like to do is start highlighting stuff. So I'm going to go back to my highlighter, okay? And I'm going to highlight the sides that I care about, right? So I need to get AC involved, all right? I need to get FG involved. I think I'm going to go with a different color here. I would alternate colors as I do this. Then I'm going to get CD involved. And then I'm going to get CF involved. Okay, and now I'm going to go back to my pen so I can actually write. And I don't want a green pen. I definitely don't want a green pen. Okay, anything but green. Anything but green. All right, so by the way, notice I kept switching back and forth between my two colors. And the reason I did that is that ultimately, whenever you have a product, okay, two portions, right, with this product, one of them is going to come from one triangle, one of them is going to come from the other triangle. Same thing over here. So if AC comes from one of the triangles, I'm proving similar. FG will come from the other one, then CD, then CF. Now, when I look at this, right, I can kind of see, all right, well, it looks like I've got kind of a right triangle here. Right triangle FGC or CGF or whatever. And I've got kind of the shorter leg of it and its hypotenuse. And then I've got another right triangle here, maybe DCA, and I've got its shorter leg and its hypotenuse. So you can already kind of see those corresponding sides. So can I possibly prove, right, that this particular right triangle, right, CDA or ADC, is congruent to this right triangle, CGF? Well, let's see what we know, right? We know we've got a rectangle. Awesome. And one thing that knowing that I've got a rectangle tells me is that this is a right angle. Okay, I know that. All right, can I get any other right angles? Well, I know that EF is perpendicular to AC. So EF is perpendicular to AC, which means this is a right angle, this is a right angle, this is a right angle, and this is a right angle. But the only one I really care about is this one, because it's within this triangle that I'd like to sort of prove similar to this triangle. So this is also a right angle. Now again, one of those right angles is based on the fact that we've got a rectangle, and one of them is based on the fact that we've got EF perpendicular to AC. Great, but I gotta still get another angle. Here's the beautiful thing though. If ABCD is a rectangle, it's also a parallelogram, right? And if it's a parallelogram, then that means that side AD is parallel to side BC. Why is that helpful? Well, it's helpful because I can then say that this particular angle and this particular angle are congruent because they are alternate interior angles. And now I've got this particular triangle, right, similar to this particular triangle by the angle-angle similarity theorem. All right, so let's outline that strategy, right? We're gonna prove two right angles congruent, right? And then we're going to get, we're gonna prove two alternate interior angles congruent. All right, then using that, we're going to prove that triangle, what do I want? ADC is similar to triangle ADC, CGF, whoops, CGF, all right, by angle, angle. All right, and then we will get the proportion. All right, we'll get the proportion we need, and then we'll cross multiply to get the product we need. Okay? Now again, this piece is important. ADC is similar to CGF. ADC is similar to CGF. Notice how I start at A with that single arc, go to D where I've got the right angle, and then go to my final angle. So on this triangle, I start with the angle with the single mark, I go to the right angle, and then I go to the final one. All right? Key that we keep those correct. It's a place where you will lose points in a proof if the letters here, the vertices here, aren't matched by the corresponding ones here. Okay, so now the proof. And this is a fairly complicated proof. It's a fairly long proof. Maybe I shouldn't say complicated, but long. All right? What I'd like you to do is pause the video now and see if you can get this proof all the way down. All right? Take a few minutes to do it. All right, let's go for it. So first things first, ABCD is a rectangle and EF is perpendicular to AC. Awesome, just a given. Okay, now, the first thing I'm going to do is I'm going to get those alternate interior angles congruent. In order to do that, though, I have to state that ABCD is a parallelogram. Why? Because all rectangles are parallelograms. We proved that in Unit 6. Now, it's great to know it's a parallelogram, but what I really need is those two sides being parallel. So I'm going to state that right now. AD is parallel to BC, right? That's that top side of the rectangle and bottom side of the rectangle. And that is literally the definition of a parallelogram. In other words, a parallelogram is a four-sided figure with opposite sides parallel. That's what it is. Or you could say, instead of a definition of a parallelogram, you could say opposite sides of a parallelogram are parallel. That's great, either way. All right, now that I've got those two parallel sides, I can get these two angles congruent, right? I can now say angle DAC is congruent to angle FCG, right? And that's because alternate interior angles created by parallel lines are congruent. Okay, I've got one of the two angles of angle. Now let's get those two right angles congruent. One thing I want to do is I want to get that right angle that's created by the perpendicular lines. So FGC is a right angle. That's this one here. Okay, and why is that? Because perpendicular segments form right angles. Okay, that's from this particular given. But I can also say that ADC is a right angle. That's my right angle here. And that's simply because of the definition of a rectangle. Remember, the definition of a rectangle is that it's a quadrilateral with four right angles. Again, instead of saying definition of a rectangle here, it's totally appropriate to just say all the angles of a rectangle are 90 degrees, or all the angles of a rectangle are right angles. All of that's good. Now, it's kind of irritating because we got to establish that both of those are a right angle before we can finally say that angle FGC is congruent to angle ADC for a duh kind of reason. All right angles are congruent. Okay, so cool. Now we have enough, right? Because we've got two angles in that larger right triangle congruent to two angles in that smaller right triangle, we can say triangle CGF is congruent to triangle ADC. Again, watch the orders of the vertices here, but that's the angle-angle similarity theorem. All right, and we're already up to 8 steps. Now, ultimately, we have to have this product, right? And so this is where it takes a little bit of nuance in terms of setting up the proportion. The proportion that we set up isn't unique, but it has to involve those 4 segments. So I can now say CD is divided by FG, all right? And again, think about that. CD is the sort of the leg of this larger right triangle, divided by FG, which is the leg of this right triangle, is equal to AC, the hypotenuse of this right triangle, divided by CF, the hypotenuse of this right triangle. That is, corresponding sides of similar triangles are proportional. And finally, let me bring this up a little bit. We can turn that proportion into the product we want. AC times FG equals CD times CF, because the product of the means is equal to the product of the extremes. That's it. That's it. A 10-line proof. A 10-line proof should never be ended by saying, well, that's it, but it is. So pause the video now and write down anything here that you may have missed. All right, great. Let's summarize. So what we looked at today were proofs that were somewhat analogous to CPC/TC proofs back from corresponding triangle work, right? Here, we were really trying to prove one product was equal to another product. And that's actually very important in geometry, as I mentioned before, especially once we start our study of circles, where similar triangles are going to play a surprisingly important role. All right. Now, in order to do that, though, in order to prove a product of 2 segments is equal to a product of another 2 segments, we typically have to prove that 2 triangles are similar that contain those 4 segments. Once we do that, we have to set up an appropriate proportion by using the idea that corresponding sides in similar triangles are proportional. Once we've got the right proportion, we then just cross-multiply to get the product that we need. And again, I'm not saying that these are necessarily easy proofs. You're going to get a lot of practice on them on the homework, obviously. All right, and we're going to see them again later on in this course. For now, I just want to thank you for joining me for another geometry lesson by eMath instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.